Hello, everyone. My name is Sandeep Singh, and I'm going to talk about Amazon Aurora DSQL. It's a distributed SQL, and it's 12 p.m., so probably we can start. So I work at Ahead as a Chicago-based company, but I live in Fishers. I'm local here, 20 miles from here. I worked at AWS. I was there for 4 years before joining Ahead, and I've been working with databases for like 20 plus years. So let's jump straight into Aurora DSQL. We're gonna talk about why we need a distributed SQL. Like why not the traditional RDBMS? And then we're gonna talk about what makes it special, and then we'll dive deeper into its architecture, how it works under the hood, and then we'll talk about its use cases, which industry it can be used. And then before you go ahead and implement DSQL, like what are things you should keep in mind, followed by a small demo. All right, so why traditional databases struggle? So I've been working on databases for like 20 years, and I've seen that in all of these traditional RDBMS databases, SQL Server, Oracle, Postgre, MySQL, they follow one common pattern where you have one write node, you can have multiple read nodes. Those multiple read nodes can work as HA or DR or simply for reporting purposes. However, there is a bottleneck on the write because you cannot scale horizontally. You can always scale vertically. And there is a limit to how much you can scale vertically, right? So that was one problem that DSQL is trying to solve. And DSQL is not the first distributed database. There have been others in the market like Cockroach Lab, Yugabyte, or Google Spanner. So DSQL is the product from AWS. It's AWS answer to distributed database. So as I said, there were challenges related to global transactions. There were challenges related to failover and operational overhead. So these are the problems we are trying to solve with Aurora DSQL. Okay, so what is DSQL? So when Amazon built DSQL, it wanted to keep the maintenance overhead of its customers. So the way it is built is it is completely serverless, meaning the compute is serverless, the storage is serverless, the internal coordination is serverless. So you don't have to worry about provisioning the resources on AWS for DSQL. And it's distributed, meaning there are more than one regions in which you can have this database, and you can, from more than one regions, you can write to the database, not just read, you can write to the database. And still, it will be consistent. So we're seeing that we have a database in, let's say, US East 1. We have the same database in US West 1. Now you have users to in both the regions, right? They're writing at the same time to the same table, and sometimes to the same row. And still, the database will be consistent. Whenever you read, you're reading the same data. So that's the magic of DSQL. So it's active as I talked about, and it is PostgreSQL compatible. So when I say PostgreSQL compatible, it's this database DSQL is built from PostgreSQL. So the core engine is PostgreSQL database. However, PostgreSQL database in its entirety cannot be distributed. So in order to make it a distributed SQL, so they have tuned some of its features. So some of its features may not be available, and AWS is working on it. However, the underlying core database engine is PostgreSQL. And then it's strongly consistent. We'll dive deeper into how it makes sure it's consistent, and it's highly available because your database is in different regions, there's multiple copies of your storage. It internally manages the high availability, so you don't have to worry about. And even if the whole region goes down, your data is safe, so it's highly available. All right, so what makes it special, right? Just in continuation to what we were talking about. This DSQL has several components working underneath. And all of these components, like the query processor, which is the compute, then the storage, then the transaction coordinator, all of these work independently. And they all can be scaled independently and automatically. So you don't have to worry about storage being full. You don't have to worry about compute bottleneck. So your compute is scaling independently. Your storage is scaling independently. The transaction coordinator is making sure all your transactions are being taken care of, whether there are millions of transactions or hundreds of transactions. And then when you have more than one write nodes, you're writing at multiple locations, right? Like multiple copies of databases. In order to make it consistent, it runs a consensus-based transaction coordination. Meaning, let's say you start a transaction in US East 1, you start transaction B in US East 2, and they both are updating the same table or the same row, that it is not committed immediately, and we'll talk about it. It does a final commit after taking into consideration all the transactions. So it does a final commit, and that after the final commit, the final data is written at both the locations, US East 1 and US East 2. So anytime a user reads the data, they read the same data. And before the final commit, if they're reading the old data, not the data which is in between the transaction started and final commit. As I said, all of these components are automatically scalable. Okay. Let's dive deeper into distributed transactions and consistency. So when we say distributed transaction, what it means is, let's say you have, in a traditional database, you have one write node, and you have users that connect to the database. They commit the transactions, they are written to the database, and it's done. That's it. Now, let's say you have one more copy of your database, and users are writing to two different databases. The copies are the same. Now, the transaction is not local. The transaction is local plus another region. Now, so that is why it is said distributed, because it's like a global transaction, not your local transaction. So, and the way it makes it work is it's going to run a consensus, and it's going to see the timestamp order of those events in different regions. And then it makes changes based on what was done first, what was done next, and what was done final. So it runs the distributed commit protocol, where it's going to commit so the global commit is like your final commit, a superset of all the local commits. And this distributed commit protocol, it makes sure all are committed or they are rolled off. So the rolled off scenarios are very rare, where you're updating rows at the same time, same data at the same time, in terms of milliseconds. And however, in order to do this globally with different regions, there are some trade-offs. And these trade-offs are because your database is located at two different geographical locations. So there are a few things that cannot be solved by technology, like the speed over geography, right? So if you have your write nodes, let's say in US East 1 and one in Europe West, let's say, so there's still a lot of distance between them. And when you're running your global transactions, there will be a latency. The latency will be the time taken by your data to travel from US East 1 to EU West 1. Now, this time taken could be 200 milliseconds, 300 milliseconds, depending on the distance between those locations. But that's the trade-off we have to live with for now, at least. And there is a coordination overhead. So it has a transaction coordinator, a component which runs automatically, which the user has no control on it. So there is a coordination overhead. It has to make sure all the transactions are taken into considerations, and the data is consistent. So when I say coordination overhead, one example is, let's say you are updating several megabytes of data in one transaction. So if you have large transactions like that, there could be latency issue because of the coordination overhead. Okay, so how does this work? And what are the steps involved? So let's say I have two regions, region A, region B, and they are both writing data. And then what happens is, when they're writing data, it goes to the global transaction coordinator, and you can see the timestamp. So in region 1, the data is written as 12 and then 100 milliseconds. And then in region 2, it is 12 and 160 milliseconds. 60? Yeah. So, but I can't see it clearly. So I think it was 120. So they are time-stamped. Every transaction is time-stamped, and then it goes to the global transaction coordinator, where it is going to look at the transaction in the order it was received, and then there is a witness region. It works as a quorum and is work on conflict resolution, and it makes sure your transactions, before there is a global commit, all of your transactions coming from different regions, they are applied in the order they were received. And it is always in sync with the AWS time sync server. So it makes sure your transactions are in the same order in which they were committed locally. Now, once the global commit is done, then it is written to the distributed transaction log, which is the storage. Now, it has a distributed transaction log, meaning that your transaction log is shared between regions. So that your, let's say if it is written to region 1, it is also replicated to region 2. And in region 2, it is then saved to your local copy in region 2, the data copy from the transaction log. So what happens is, after the global commit in the global transaction coordinator, the same data is being read no matter from where you're reading it. And this is the timeline of this the distributed transactions that's happening. And I'll pause here for a second if anyone has any questions, and then I can move forward. All good. Okay, so now we know that it's a distributed database, right? So there's a specific use case for this. So there are businesses where it is required, and that makes life easier for those businesses. For example, in global SaaS platforms, for example, if you have an ERP application that runs across US, and you have users in US East 1, US West 1, West 2, and then you want to make sure they can write locally to the database, they can use DSQL. And then there are financial systems. If you have banks that run transactions across countries globally, then they don't have to have different databases, and they can have the same database, DSQL, and the internal the syncing will take place automatically for them. So no matter where you do your banking transaction, it'll be taken care of by DSQL internally to keep them in sync and consistent. Similarly, airline or travel reservation systems, where several users are booking tickets at the same time globally. And then you have gaming backend. So nowadays, people play games with users who are geographic, geographically different regions. So what happens is if they have to maintain a global leaderboard for the games, this is an apt use case for DSQL, where it can maintain the global leaderboard for its players from different regions. And also e-commerce platforms like Amazon. Okay, so now that we know DSQL is great, it's very useful in those use cases. But what do we need to keep in mind before we go ahead and implement it or do a POC? So one is the latency expectations. So if your application is very sensitive to sub-millisecond latency, then probably this is not the best database. And then your application has, let's say, hot rows. Hot rows meaning the same row is being updated very frequently, like hundreds of updates within a minute, within seconds. If you have application which has hot rows, then probably it's not a good idea to go ahead and implement DSQL and wait for any updates from AWS on that. And then transaction patterns. So let's say your transactions, as I said, if your transactions have several megabytes of data changing, or if your transactions have several steps, like 20 steps, 20 changes in one transaction, those kind of transactions, maybe DSQL is not the right database for those transactions, because that will have an overhead on transaction coordination and the distributed commit. So, and then the most important one, the PostgreSQL compatibility. So I was talking about the DSQL is built from PostgreSQL, not on top of, but from PostgreSQL, meaning by changing PostgreSQL's architecture, the internal architecture. So in order to achieve these features of global transactions, distributed database, they have to forego some of the features. And some of these are, they may be very important for your applications, like foreign keys. Foreign keys are not supported. Then temporary tables are not supported. Stored procedures are not supported. User-defined functions are supported. I want to make sure. And then the Postgre extensions. So Postgre is a community database, and they keep building extensions for some specific purpose, right? So those Postgre extensions, they are not supported yet. So please make sure your application is not using any of these. And if it is, then a good idea would be to, for example, almost all the applications use stored procedures, right? So what you need to do is make sure the business logic is moved to the application before you implement a DSQL. And operational maturity, that's obvious. It's new. It was launched just a year ago. So they'll take a few years or maybe a few months for the operational maturity. All right. Was it time? Okay, we have it. Okay. So I'm going to do a small demo to show how it's working. So what I'll do is I'll create a test table, and then I'm going to update the rows from two different regions, and then I'm going to show you that it's consistent. So no matter from which region you update it, you see the same data. Oh, sorry. So let me connect to my AWS console, and I'll connect again in a second once I'm logged in. All right, so you can see this is my AWS console. I'm logged into AWS console, and let me expand it. Okay, so I'm in region, this is Ohio, UCS 2, and you have this DSQL database, which is DSQL cluster 2. And the other cluster is in Oregon region, US West 2. So if you go there, I have this demo SQL cluster 1 here. Now they are both part of the same DSQL cluster. So if you click here And if you go at peers, you can see that US East to Ohio region, this is its peer, and North Virginia is the witness. Now, what I'm going to do is, so there's a query editor. I'll go to query editor in my cluster 1, and I'm going to run some scripts. Okay, so let's create a table here. All right, so table is created. Let's insert some data. All right, and let's see if the data is really inserted. Yes. All right, so you can see this is the demo cluster 1, and this is in US West Oregon region. And you can see 3 rows there. And you can see now what we're going to do is before update, let me go and check if this data is also present in US East to the other region. So let me just copy this. And I have not made any changes in US East 2, only in US West Oregon region. All right, so we created table already. I'm not going to create it here. Let's just say if I can see the data. All right, so as you can see, I added the data in the other region, but I can see it from this region. And they have their own databases, like it's not shared one. So the data got replicated from US West to US East 2. Now what I'm gonna do is I'll go ahead and make some changes in the data, some updates. So I'll make an update in region 1, and then I'll make an update in region 2, and then I'll see what's the final update. So let's go back to my region 1 is US West, so I'll go there. So what it's doing is it's setting the order status to processing where order ID is 1001. All right, and let's verify it. So you can see the first row, it changed to processing. And let's go back and to the other region and make the update from that side. So what we're doing here is for the other 1002, we are changing it to shipped. Okay, this got updated as well, and this got updated in. So 2 updates, they are being done in 2 different regions. So you can see the second row has changed to shipped. And as you can see, the updates, the previous update processing is showing here. The second update shipped, that is also showing here. So both of our updates, you can see in both the regions. And you can see the timestamp when they were changed. So what I was trying to show is a very simple example. And what it's trying to show is if you have updates being done from different regions, they'll be applied to your table in the order in which they were done. And this order is maintained by the global transaction coordinator. So that takes care of this distributed transactions. All right, let's get back to this. Okay. All right. So yeah, that is all I wanted to show today. And I'm open for questions. So when I was talking about consistency, I was talking about how it maintains consistency when you're writing from more than one nodes. So when you talk about use case, it's actually the business use case, right? So Aurora, if you talk about just Aurora PostgreSQL or MySQL, so in those cases, you still have just one write node. So when you're writing something, it goes to just one node, and there is no way you can write to another node. So, and with Aurora MySQL or Aurora PostgreSQL, you don't have to worry about distributed transactions or consistency issues because it's all being done at one place. Yeah, so it's basically if your business use case requires you to write at multiple locations, then DSQL makes sure it is consistent. And that is all for the day. Thank you.